Hi, this is Somaiah, working as assistant professor in the Department of Mechanical Engineering at Institute of Aeronautical Engineering, Hyderabad. Today, as part of fluid mechanics and hydraulic missions, I am going to discuss the velocity and acceleration of the fluid particles in a fluid kinematics. Two basic and important field variables in the study of fluid mechanics are the velocity and acceleration of a fluid. So, in order to find out various characteristics, we need velocity and acceleration, and the other fluid characteristics will also be affected due to the variation in velocity and acceleration. So, therefore, we'll see how to find out its velocity and acceleration about three-dimensional plane and about two-dimensional plane also, so that the velocity vector also acceleration vectors is a characteristic once identified, then we will be defining various other parameters also will be useful for defining and to analyze the other parameters too. So in velocity field, the important parameter governing a flow field is the velocity. Other field variables such as the pressure, temperature also influenced by the velocity. So in general, the velocity is a function of both location and time. The motion of a fluid like that of solid is described quantitatively in terms of characteristic known as velocity. So here, basically the velocity can be defined for fluids such as air, liquids, and for solids also we'll define the velocity, but for solids the velocity will be defined as a whole. But in case of fluids, for a particular fluid particle for which selected particle, we'll define the velocity, and we will trace out its path throughout its path, how the velocity, its way, direction and magnitude is going to be changed, and with respect to the steady flow, in steady flow, how the velocity is taking place. In case of steady flow, the variations will be constant. Variation should not be there with respect to the time, but in case of unsteady flow, there will be a lot of variations. So in case of uniform flow, the velocity should become constant, but whereas in case of unsteady flow, the velocity will vary with respect to the time in space, with the time to time. But so in these such type of flow fluid fields, we have to define the velocity. We are supposed to calculate the velocity for a selected particle. Therefore, the velocity at any point of a fluid mass is expressed as the ratio between the displacement of a fluid element along its path and a corresponding increment of time as a later approaches to zero. The change in time as approaching zero will be defining the velocity. A particular point in the space occupied by a fluid in motion is selected, which may be denoted by the coordinates x, y, z in case of three-dimensional plane. So in case of if a fluid particle is selected for a 3D plane, so for which the Cartesian coordinate system where the location of the fluid particle will be identified, and about which we have to resolve the velocity along three directions. Then we'll be finding out the velocity about three respective directions. So here, about x, the location at a small x, it is located from x direction, from origin. About a small x, it is located, and about y direction at small y, and similarly at j direction for small d. So here the location is the fluid particle selected in 3D plane at this location, where the coordinate, its position is denoted by xyz. So about xyz, it is denoted as the fluid particle is taking a curved path. So for which if you draw a tangent for a curved path, if you draw a tangent, then that indicates the direction of the velocity vector. So here similarly, if you as the velocity vector is a tangent to the curved path, we can resolve this position from the position beginning at t equal to 1, at t equal to 2. This is the position. So the position is varying. So for this position, then you can take the dx as a displacement about x direction, and dy is the displacement about y direction. Similarly, dz is the displacement in z direction. So ds is the change in the position ds. So there is a ds. So and there is an angle about theta. The magnitude will be theta with respect to x. So you can identify, you can measure the velocity components about three different directions. Since this point is fixed in space, the coordinate x, y, z and the time t are independent variables. At this point, if ds is a distance traveled by a fluid particle in time dt, then velocity v of the fluid particle at this point may be expressed as, velocity can be expressed as a limit of ds over dt as dt approaching 0. The velocity expression is limit of ds by dt, that is change in position with respect to the change in time, as the time elapsed time dt indicates the elapsed time approaching 0. So the velocity is a vector quantity, and hence it has a magnitude as well as direction. Therefore, the velocity v at any point in fluid can be resolved into three components and three mutually along x, y, z directions. So as the velocity is a vector quantity, it will have both direction and velocity, and based on the steady flow or unsteady flow, uniform or non-uniform, then the velocity may vary or may not vary based on the flow field selected and remaining parameters also. But the velocity components u, v, w, its respect to along its respective directions x, y, z can be divided and can be calculated. So each of these components can also be expressed as a limiting rate of displacement in the corresponding direction. So where dx, dy, dz are the components of the displacement ds. So it can be expressed u, the velocity component v is divided into three directions, where component velocities are u, v, w about x, y, and z directions. So it can be expressed as a limit of dx by dt as elapsed time approaches 0 about x. Similarly, v also limit of dy by dt as dt approaches 0, then limit of dz by dt as dt approaches 0. So this is about z direction. So in with respect to each and every direction, the component velocity can be calculated by using these equations about x, y, z directions. Since the velocity v at any point in a flowing mass of fluid in general depends on x, y, z, that is the coordinate position of the point under consideration the time t with respect to the time. So we have to consider the particular flow field with respect to the time, whether the parameters, the velocity components about x, y, z directions are going to vary or not. Therefore, the components u, v, w will also in general depend on x, y, z and time t. Hence, the velocity v and its components u, v, w may be expressed in terms of functional relationships. So before going to calculate the velocity and its velocity components about x, y, z directions in case of 3D plane, so we have to understand its functional relationships. So after deriving the velocity expressions, then we will go for solving a problem for a particular fluid particle for a given parameters, and we'll be calculating the velocity components. So u is f1 of x, y, z, t. Similarly, v equals to f2 of x, y, z, t. Then w is f3 of x, y, z, t. These are the functional relationships as they are dependent. They are time dependent, and their velocity components are also dependent on these three mutually perpendicular directions. So in vector notation, the velocity v may be expressed in terms of ui plus Vj plus Wk. Capital V, the velocity vector can be denoted as Ui plus Vj plus Wk. So where I, J, K are unit vectors, and U, V, W are velocity components with its respective axis. And the resultant velocity can be calculated. The resultant velocity is root of U square plus V square plus W square. So with this expression, we can calculate the velocity of a particular fluid particle for a given time period. For a particular point, since the coordinates x, y, z may be regarded constant, the above expressions will indicate how u, v, w vary as the time t varies. On the other hand, if time t regarded constant, then since x, y, z may represent any point in the flowing mass of fluid, the above expression will indicate how u, v, w vary at different points. Then we are going to discuss the acceleration. Once the velocity of a fluid particle is measured, then the rate of change of velocity is simply called as acceleration. Here we will we are going to define what is temporary or temporal acceleration, convective acceleration, and how the acceleration will be varying about a streamline, whether it is going to follow the velocity direction or not. All these things we will find, we will see in this case. So in acceleration, if you know these differences between the velocity, acceleration, and types of acceleration, then we will be finding out its a particular magnitude or particular acceleration. Acceleration is defined as the rate of change of velocity with respect to the time. So, as stated earlier, the velocity of a fluid particle is a function of the positions point with respect to the time. So, in simple, the acceleration of a fluid particle can be defined as change of velocity with respect to the time. Thus, if certain fluid particle has a velocity v, capital V, which has u, v, and w as three components about its three axes x, y, z, then they can be expressed. The acceleration about x direction can be expressed as a limit of du over dt as elapsed time dt approaching 0. So this is the acceleration expression about x direction. Then acceleration about y direction is the limit of dv over dt as dt approaching 0. Similarly, a limit of dw by dt as dt is approaching 0. So this is about z direction. Velocity component about z direction is w. So with respect to the time, rate of change of velocity with respect to the time as elapsed time approaching 0. These are the three expressions of acceleration about x, y, and z directions. But u equals to f of x, y, z, t, and hence the total substantial derivative of u with respect to the time is you can find out by using the chain rule of differentiation. So ax equals to du by dt. So rate of change of velocity with respect to the time about x direction, that is du by dt, but by chain rule of differentiation, as it is dependent of x, y, z, and t, these variables, by applying the chain rule of differentiation, we can expand the acceleration component about x direction is dou u by dou x into dx by dt plus dou u by dou y into dy by dt plus dou u by dou z into dz by dt plus dou u by dou t. So with respect to the time, so we'll expand the acceleration component about x. So but here we have to assume dx by we have to consider dx by dt is small u. Similarly, dy by dt is v, dy by dt is v, dx by dt is small u. So dz by dt is small w. So you have to substitute these equations. You substitute. You can replace with uvw, so that ax becomes u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dou t. So in case of a unsteady flow. Similarly, we will calculate acceleration of a component about y direction also. In similar way, Ay is equals to dy by dt, so it can be expanded by chain rule of differentiation, and you can substitute dou u by dou x, dou v by dou y plus dou w by dou z, so that you will be getting dou u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z plus dou v by dou t. So this is about y direction, and similarly the acceleration about z direction is also derived in the similar manner. So that is u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z plus dou w by dou t. So this is in case of unsteady flow. So we have to consider dou w plus dou w by dou t plus dou v by dou t plus dou u by dou t also. But in case of, if you consider the steady flow field, in steady flow field, so dou v by dou t equals to 0. Therefore, its resultant velocity components also becomes 0. So dou u by dou t becomes 0, and dou v by dou t also 0. Dou w by dou t also approaching 0. So therefore, you can reduce the above derived expressions for acceleration about three different directions like this. So ax equals to u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. So where here we have removed dou u by dou t. So as it is a steady flow field with respect to the time, so that becomes 0. Therefore, that is removed. In similar way, the for y direction acceleration about y direction also, in acceleration about z direction also. So the dou w by dou t becomes 0, dou v by dou t has become 0. Therefore, the acceleration in steady flow field can be defined by using these three equations about x, y, and z directions. Acceleration components about three mutually perpendicular directions. So therefore, after deriving the acceleration components for x direction, y direction, z direction, for steady flow, for unsteady flow, so then the velocity like velocity vector, we have to find out the acceleration vector too. So the acceleration vector can be defined as axi plus ayj plus az into k. So this is the acceleration expression in a vector form. So its resultant acceleration can be calculated by root of ax square plus ay square plus az square. In the above expressions, dou u by dou t, dou v by dou t plus dou w by dou t represents the rate of increase of velocity with respect to the time at a particular point in the flow field, and hence it is known as local acceleration or temporal acceleration. So the local acceleration and temporal acceleration components are dou u by dou t, dou v by dou t, and dou w by dou t with respect to the xyz directions. These are called as local acceleration components. The remaining terms in the above expressions represents the rate of increase of velocity due to the particles change of position, and hence it is known as convective acceleration. So there are two components. One is local acceleration, another one is convective acceleration. So where the local acceleration components are dou w by dou t, dou u by dou t, etc. So but the remaining components in the velocity components in the acceleration expression becomes the convective uh, acceleration components. Convective acceleration. In steady flow, the local acceleration is 0, but the convective acceleration need not to be 0. So that we have to remember, as it is a steady flow, the local components, these three components will be 0, but remaining parameters will not be. So if you go back to this slide, the remaining parameters need not to be 0. So in steady flow, so that we have to remember, and the total substantial acceleration is not necessarily zero, because as convective acceleration is not becoming zero, so therefore the total acceleration may not be zero, but only the local acceleration component becomes zero. In case of uniform flow, the convective acceleration is also zero. Therefore, total acceleration becomes zero. So for uniform flow, the velocity, as the velocity remains constant, the convective also becoming zero, along with the local acceleration component. Therefore, the total acceleration becomes zero. Like velocity, the acceleration is also a vector quantity. So both are vector quantities. However, unlike velocity vector, the acceleration vector has no specific orientation. So if there is a fluid particle is following this curved path, the velocity vector will be tangent to this curve. So this is velocity vector. So this is a fluid particle moving along with a streamline. So, but the acceleration need not to take this same orientation. It may be different orientation. Sometimes it may be normal to this fluid particle also. It may be take different orientation also. So, therefore, the acceleration need not to follow the orientation of the velocity vector. With respect to streamline, so it need not to always tangential to streamline. In other words, the acceleration vector may have any direction, so that at any point it has components both tangential and normal to the streamline. So one it will have both the components. One is a tangential, another one is a normal. Normal acceleration will be there, and tangential acceleration will also be there. So therefore, it will have any direction. It will have both the components at the same time. It will have both the components with respect to a streamline. It need not to follow the the velocity vector direction. The tangential acceleration is developed for a fluid particle when the magnitude of the velocity changes with respect to the space and time. So the tangential velocity is developed when magnitude of velocity changing. The tangential acceleration will be connected with the magnitude of the velocity. When magnitude of the velocity changes, tangential acceleration changes. So the tangential acceleration is not connected with the direction of the velocity, but normal acceleration will be connected with the direction of the fluid particle. So these two are connected. Hence, a normal acceleration may be developed simply due to the change in the direction of the velocity of the fluid particle, regardless whether the magnitude of the velocity is changing or not, whether it changes or not. But the normal acceleration depends on the change in the direction of velocity only. The accelerations AS and AN in the tangential and normal directions, they can be expressed by the following expressions. The AS is a tangential acceleration will be defined as a limit of dvs over dt as dt approaching 0. Similarly, the acceleration about normal direction is an is equals to limit of dvn by dt as dt approaching 0. So here we can understand how the fluid particle is moving over a streamline. You say this curved line is a streamline, and about its tangential direction, the component, the tangential acceleration component will move. You can be find you can find about tangential direction, but about normal direction, you can find the normal acceleration component an. So then there will be a direction of acceleration. So like this, you can express as and an. The as is about the velocity about the streamline over change in time dvs by dt, and the normal component about this normal vector dvn, change in velocity about normal to the streamline, so with respect to the change in time. So these are the two different acceleration components when the velocity when it is changing in magnitude and when it is changing in direction. Okay, so therefore these are the two components. And here in acceleration, we have to remember about local and convective accelerations, and the acceleration components along tangential direction to the streamline, along normal direction to the streamline. So in this table, we can remember, we can recognize, so type of acceleration will be taking place according to the is a streamline pattern. If the streamline is straight and parallel like this, if it is straight and parallel, all are like laminar flow, the all fluid particles are moving one over another without disrupting others paths, then such in such cases no acceleration will be taking place. So no acceleration means there is no convective and there is no a local acceleration component. If the fluid is straight converging streamlines, if the fluid is straight converging like this, if it is gradually converging in case of venturimeter, etc., in some cases, then you will be finding out there will be convective tangential acceleration can be recognized in case of converging streamline pattern. The streamline pattern should be converging type. So in that case, we will be identifying the convective tangential acceleration. The concentric streamline pattern, if the streamline pattern is like this in a curved concentric path, so and then what happens, there will be a convective normal acceleration can be identified. So but whereas curved converging will be there, both the tangential, so along with the normal component, both acceleration components can be recognized. So in this example, we will be trying to finding out the velocity vector and the magnitude of the velocity, also its direction along with the acceleration components. We'll try to find out. So the velocity vector in a fluid flow is given by 4x cube I minus 10x square yj plus 2tk. Find the velocity and acceleration of a fluid particle at 213 about xyz directions. Their coordinates are 213 at a time t equals to 1. So for this case, we have to calculate the velocity and acceleration vectors. So the velocity components you can take from the given expression. U becomes 4x cube, and similarly y equals to minus 10x square y. W becomes 2t. The 2t is the w. So initially, when u, v, w are identified, we know the coordinate, the position of a fluid particle with respect to three-dimensional plane. It is given at 2, 1, 3 from x, y, z. From x, y, z. So therefore, we can calculate the number of units, velocity units in x direction, y direction, and z direction also. As it is 4x cube, you will get 4 into 2 cube, therefore 32 units. Similarly, v equals to minus 40 units, w is 2 units. So y is moving in a negative direction. The velocity vector at 213 can be written as 32i minus 40j plus 2k. So this is the velocity vector. So but the resultant velocity you can calculate by using this expression, root of u square plus v square plus w square. So from this, u becomes 32, where v has minus 40, w is 22, 2 square. 2 square, this is 2 square, not 22. So where w equals to 2, where so as u equals to 4x cube and v equals to minus 10x square y, w equals to 2k, 2tk, as it is 2t, t equals to 1 is given, therefore it becomes 2 units. And if you substitute this equation, in this equation you will get the velocity vector as 32i minus 40j plus 2k. So therefore, if you want the resultant velocity, this becomes 51.26 units. You have to substitute 32 and 40 and 2. Similarly, the acceleration is given by ax equals to this expression we have derived for a unsteady flow, because t equals to 1 is given, as the t equals to 1 is provided, you can call it as unsteady flow. Therefore you add dou u by dou t, dou v by dou t, and dou w by dou t also. So, and before going to calculating the acceleration components about x, y, z directions, you can calculate dou u by dou x, because u is known, u, v, w are known, dou u by dou y, dou w by dou z, dou u by dou t. Similarly, dou v by dou x, dou v by dou y, dou v by dou z, and dou v by dou t. Similarly, these components also, if you calculate before going into substitution, then it becomes simple to calculate the acceleration components. Then dou u by dou x is 12x square, dou u by dou y is 0, then dou u by dou z, dou w by dou t also 0. So like this you have to differentiate the given expressions. Then we will be noting down all these equations. So if you, after calculating the velocity components, the velocity differential component with respect to various axes, then we will substitute into the given expression. The expression is ax is 4x cube into 12x square plus minus of 10x square y. So this is v. So you have to, this is nothing but we are substituting the dou u by dou x, dou u by dou y, dou w by dou u by dou z, dou u by dou t in this expressions, u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dou t. So here we are substitution. We are doing substitution in these expressions. So after substitution, you will get 48 x power 5, and then it will be 48 into 2 power 5 as x equals to 2. So then this is equals to 1536 units, 1536 units. Acceleration component about x direction. So similarly, if you substitute the velocity components about y direction, about in the expression of ay, then so you will be getting this expression. So after simplification, you will get minus 80 x power 4 y plus 100 x power 4 y minus. So you can substitute as x equals to 2, y equals to 1, x equals to 2. Here also y is 1. So just you have to calculate the velocity component with respect to different axes, and you have to substitute in the its respective equation. Then we will be knowing the acceleration about y direction is 320 units. Similarly, about az, the we have to substitute the velocity components about az expression. If you substitute, then you will be getting the 2 units about z direction. The acceleration about x, y, z are calculated. Once it is known, then you can substitute those values into a vector form, so that you will be getting the acceleration vector. Acceleration vector is axi plus ayj plus azk. So since ax is 36 plus 320j plus 2k, so this is called as the acceleration vector. Similarly, the resultant acceleration can be calculated as root of ax square plus ay square plus az square. So then we will be getting 1568.9 units. So this is the how to get the acceleration, how to get the velocity of a given fluid particle in a flow field with respect to the unsteady flow. So if it is steady flow, dou u by dou t, dou v by dou t, dou w by dou t becomes 0. Based on that flow field, you have to write the expressions of acceleration and then go for calculating the respective acceleration components and substitute them into a vector form. Similarly, substitute them to get it to a resultant acceleration also. So these are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.